To handle a wider range of indeterminate structures, we need to develop some basic conventions. The basic information required for any analysis is the following. Firstly, the degree of statical indeterminacy, alpha. Secondly, the number of critical sections, C. 3, a sign convention. And 4, the number of elementary mechanisms that develop, given by n equal to C minus alpha. From what we've covered so far, we already know 1 and 2, so we need to discuss a bit further the sign convention and the number of elementary mechanisms. To develop a sign convention on a structure, we construct an internal boundary. This is shown here by a dotted line. And this dotted line is drawn on the interior of the structure. During collapse, any motion that causes an angular extension relative to this boundary generates a positive angle. To make this more clear, consider this hinge taken from somewhere in a collapsed structure. In its uncollapsed state, the dotted line is lying beneath the structure, and what we are seeing is the development of a positive angle. This is because an extension in the angle between the two segments develops. Another way of looking at this is that the structure shown in the dark line, when it's in its deformed state, never crosses the dotted line. On the other hand, for the same segment of structure, if it collapses in the other direction, then we can say a contracted angle is formed, or part of the structure shown in the dark line crosses the dotted line. Finally, in terms of the bending moment sign convention, the bending moment is positive on the tension side. Elementary mechanisms are mechanisms that cannot be made by combining any other mechanism. They are mechanisms that are independent of each other. For example, consider the continuous beam. This is a 3-span continuous beam with loads in each span and loaded at points A, B, C, D, E, F, and G. In this scenario, we can construct 3 basic mechanisms. Corresponding deformation angles, 2 theta and minus theta. For the second mechanism, we have a similar result, and also for the third mechanism. If we then tabulate the deformation angles at their corresponding locations, we can see that if we try and add up these deformation angles, it is not possible to make any of the three mechanisms from adding these up, or any two of them. This is what we mean by independent mechanisms. By contrast, a combined mechanism is a combination of two or more elementary mechanisms. To understand combined mechanisms, consider the following portal frame structure. The first mechanism is what we call a beam mechanism, where three plastic hinges form across the top beam. This results in deformation angles minus theta, 2 theta, and minus theta at locations B, C, and D. The next elementary mechanism is what we call a sway mechanism, with deformation angles at plastic hinges at locations A, B, D, and E. If we put these into a table of deformation angles, and then add up the contributions vertically, we find that we get a combined mechanism with an angle minus theta at A, no deformations at B, an angle of 2 theta at C, minus 2 theta at D, and theta at E. And this is drawn in the third diagram above. The general procedure for calculation of the load factor at collapse is outlined as follows. Firstly, as before, we need to find alpha. We then need to find the number of critical sections C. We then need to find the number of independent mechanisms N, after which we then use the kinematic method. With the kinematic method, we evaluate lambda for each independent mechanism. We then select the mechanism with the lowest lambda or highest MP and perform static checks. If the yield condition is not satisfied, then we evaluate the combined mechanisms to obtain a lower lambda. This method is best illustrated using an example. The example we have here is a rectangular portal frame with a plastic moment capacity for all sections at 30 kilonewton meters. It's loaded laterally by a load 16 lambda and vertically at the center of the beam by a load 8 lambda. In order to proceed with our analysis, we need to first gather together all the necessary key data. We need to set up our sign convention. And then we need to identify the number of critical sections. We have critical sections at the supports, at the joints, and where the concentrated loads are applied. Lowercase n is equal to 3, as this is a planar frame. We have 3 members, 4 joints, 6 reactions, because this is a fixed-based portal frame, and we have 0 pins. As a result, alpha is equal to 3 times 3 minus 4 plus 6 minus 0, which is equal to 3. We've identified 5 critical sections, so n is equal to C minus alpha, which is equal to 2. So there are 2 elementary mechanisms with this structure. The first elementary mechanism is what we call a beam mechanism. And this shows a vertical state of collapse under the concentrated load 8 lambda. We have plastic hinges at B, C, and D with corresponding deformation angles minus theta, and in the center 2 theta. Noting that the angle in the center, 2 theta, is positive because it creates an extension, and the angles at the ends being negative because this structure crossed the dotted line at those points. Under the concentrated load, we have a vertical displacement delta C, comma V. The deformation angles then are summarized in a table as being 0, minus theta, 2 theta, minus theta, and 0. Considering first the displacements under the horizontal load at B are 0, and the displacements under the vertical load are just the length of the section that's undergoing the displacement times by the displacement angle, which in this case is 5 times by theta. Considering now the balance of energy, or as we will now call virtual work, we equate the work done by the applied loads with the internal work done at the hinges. Prior to collapse, this is given by 8 lambda times by delta C, comma V, and that's equal to the moments at B times by their rotation, minus theta, plus the moments at C times by their rotation, 2 theta, plus the moments at D times by their rotation, minus theta. At collapse, we have 8 times by lambda C times by 5 theta, substituting in the delta CV, and this time we replace the moments MB, MC, and MD with their corresponding cross-section plastic moment values, adopting the same sign as the angle of deformation. In this case, we have minus MP times by minus theta, plus MP times by 2 theta, minus MP times by minus theta. When you add all of those up, they equal to 4 MP theta. Solving then for the plastic collapse load factor for this mechanism, we get lambda 1 equal to MP over 10, or substituting the value for MP, which is 30, we get 3. So therefore, lambda 1 is equal to 3, and the potential collapse load factor is less than or equal to 3. The second mechanism is a sway mechanism. This has plastic hinges at A, B, D, and E, and corresponding deformation angles minus theta, theta, minus theta, and theta, and a horizontal displacement under the load of delta B subscript H. We can then summarize these angles in a table. So you have minus theta, theta, 0, minus theta, and theta. The horizontal displacement. The horizontal displacement, delta BH, is equal to 4 times theta, and the vertical displacement, dCV, is equal to 0. Applying virtual work, again, we have 16 lambda times by delta BH, and this time that's equal to MA times minus theta plus MB times by theta plus MD times by minus theta plus ME times by theta. At collapse, we then have 16 lambda times by 4 theta, and that's equal to minus MP minus theta plus MP times by theta minus MP times by minus theta plus MP times by theta, which sums up to 4 MP theta. Solving then for the collapse load factor for this mechanism, we get 4 over 64 times by MP, or substituting in for MP, 1.875. Therefore, lambda 2 is equal to 1.875, and the plastic collapse load factor, lambda C, is less than or equal to 1.875. At this stage, we need to perform static checks on mechanism 2, as mechanism 2 is producing the lowest collapse load factor. The way in which we do this is to return to the virtual work equation for mechanism 1, and we substitute in the values of moment and plastic collapse load factor for mechanism 2. So the equation that we are looking at is this equation, and we note that the only unknown quantity is MC. If we look at the sway mechanism, we've evaluated the moments A, B, D and E, and we have said they are all MP. But with that plastic collapse load factor of 1.875, we need to evaluate what the moments would be at C. So in order to do that, we use the equation for collapse mechanism 1, because that features the moments at C. So 8 lambda times by 5 theta is equal to MB times minus theta plus MC times by 2 theta plus MD times by minus theta. For mechanism 2, MB is equal to MP and MD is equal to minus MP. MC is currently unknown. We also know that lambda is equal to 1.875. So performing this calculation, we have 8 times by 1.875 times by 5 theta equal to MP times minus theta plus MC times 2 theta minus MP times minus theta. evaluating this, noting that we have values for MP, we can then say that MC is equal to 37.5 kilonewton meters, which is greater than MP. So, for a plastic collapse load factor from mechanism 2, where the plastic collapse load factor is equal to 1.875, we can say that we have a yield violation at MC. We now need to use the results of mechanism 2 and invoke what we call the lower bound theorem, which involves scaling the collapse load factor down. To do this, we say we divide MC by MP, which gives us 37.5 divided by 30, and that equals 1.25. We can then produce a new load factor. We'll call this lambda 2 start to indicate that it is new, but it's still based on lambda 2. And we get 1.875 divided by 1.25. And that gives us a value of 1.5. If we now scale the bending moments accordingly, we find we get MA equal to minus 24 kilonewton meters, MB equal to 24, MC equal to 30, MD equal to minus 24, and ME equal to 24. We can see here that only one of these bending moments achieves the full plastic collapse capacity, which means that all of these other moments are under the plastic collapse capacity, and as a consequence of this, no plastic hinges will form at these locations. One plastic hinge is not sufficient to form a plastic collapse mechanism, so whilst we have satisfied equilibrium and yield, we do not satisfy the requirement for a plastic collapse mechanism to exist. The final step then is to produce what we call the combined mechanism. With the combined mechanism, we sum up the angles that were produced in the table above to determine the final combined collapse mechanism. So we have mechanism 1, mechanism 2, and the combined mechanism. As before, we have angles 0, minus theta, 2 theta, minus theta and 0. We have minus theta, theta, 0, minus theta and theta. Adding up then the columns, we find we've got minus theta, 0, 2 theta, minus 2 theta and theta. So the combined collapse mechanism will look like this, with no deformations at point B, plastic hinges at all other locations, with angles minus theta, 2 theta, minus theta and minus theta, and theta. We have both horizontal displacements at B and vertical displacements at C. under the loads 16 lambda and 8 lambda. The displacements are then dB, h equal to 4 theta, and delta B, delta C, v equal to 5 theta. Evaluating the virtual work equation, we find we have the external work being 16 lambda times by 4 theta for the horizontal part, plus 8 lambda times 5 theta for the vertical part, and that's equated to MA times minus theta plus MC times by 2 theta plus MD times by minus 2 theta plus ME times by theta. At collapse, we then have 104 times by lambda theta equal to 6 MP theta. This is due to minus MP times by minus theta plus MP 2 theta minus MP minus 2 theta plus MP theta. So evaluating lambda, we have lambda 3 equal to 1.731, such that the plastic collapse load factor is less than or equal to 1.731. Finally, again, we need to perform static checks. Looking at this equation, we can see that we have values for MA, MC, MD and ME, but MB is unknown. So partially constructing our bending moment diagram for this structure, we can see that we know that MA is equal to minus MP. We know that MC is equal to MP, and at MD this is equal to minus MP, and ME is equal to MP. MB remains unknown. We now need to use an equation which features MB, which in this case is again the equation from the first plastic collapse mechanism, but this time we substitute in the updated value of lambda. So we can say that 8 times lambda 3 times by 5 theta is equal to MB times by minus theta plus MP times 2 theta minus MP times by minus theta, or 8 times 1.731 times by 5 theta is equal to MB times minus theta plus 30 times 2 theta minus 30 times theta. So MB is equal to 20.77 kilonewton meters, which is less than MP. As a result of this, we are not seeing any violations in the yield moment, so we can say that lambda C equal to 1 0.731 is the true plastic collapse load factor.